So again, the arc length formula for, you've got some curve, y equals f of x. You want to find how long that curve is between the x coordinates a and b. Well, then your length, capital L in this formula, is going to be the integral from a to b of the square root of 1 plus f prime of x squared, all dx. Now, if you prefer, I could have done this slightly differently back when I still had the delta x squared and the delta y squared, and I could say, let's just divide everything by delta x squared. What would that look like? Well, underneath my square root sign, I'd have 1 plus delta y on delta x squared, and I could factor a delta x out of the whole square root. And in the limit, I know that I'd get my dy on dx. That's just another name for the derivative. Outside of that, I'd have my dx differential. Another way to think about it. So here I have a slightly different formulation, integral a to b, square root of quantity 1 plus dy squared on dx squared, all dx. This can become helpful for later on when we are looking at curves that have implicit differentiation going on. So curves that aren't necessarily the graphs of functions. Okay, let's calculate. Find the length of the arc of the, vocabulary, who cares? Of the function, not a function, y squared equals x cubed between the points 1, 1 and 4, 8. Here's my picture. So the entire curve has been drawn in blue. The segment that I care about has been drawn in pink. And already I need implicit differentiation. Y squared equals x cubed. That's not a function of x. Okay, well, top half of the curve, I could say that y equals x to the 3/2 power. All right, fine, that is a function. dy dx then is going to be 3/2 x to the 1/2 power. Simple power rule. So I put that into my formula. The arc length formula is going to be L equals, you do need an equals sign there. L equals the integral here from 1 to 4. My integrand is the square root of quantity 1 plus dy on dx squared, all dx. So for us, that becomes integral from 1 to 4, square root of quantity 1 plus 9/4 x, all dx. Oh, very nice. So having to square there actually makes it a bit easier. And, well, I'll just do a u sub on this. Let's say u equals 1 plus 9/4 x, du equals 9/4 dx. Since I'm doing a definite integral with a u substitution, I need to change my bounds. And x equals 1 means that u starts at 13/4, and x equals 4 means that u finishes at 10. So I'm really just integrating this function from 3/4 up to 10. My integrand is now the square root of u because we factored out a 4/9. Fundamental theorem of calculus says use our antiderivative 2/3 u to the 3/2 power. Evaluated the endpoints and we get this figure. 1/27 of the quantity, 80 roots of 10 minus 13 roots of 13. Okay, fine. That expression certainly defines a real number. If I wanted to, I could find a decimal expansion, but I don't, so I won't. What I want to emphasize, I am being a little bit glib, I apologize for that. What I want to emphasize here is the use of the arc length formula and the use of the pictures. Once I have my derivative, everything after that is just an ordinary integral. The difference now is that the integral is representing length rather than integrals which represent area or integrals which represent volume. But that's okay. Numbers can mean different things.